Hi, I'm Byung-Gyu Ahn. I'm a graduate student from JHU. And during the workshop, I worked on beam search. And the repeating theme in our talk and the goal of beam search is to improve speed with minimal loss in accuracy. So, in beam approach, we focus on pruning constituent in each cell chart. So how we do is to greatly eliminate less probable constituents during building the chart. So it's a standard beam search approach, as in Collins' paper. And the question here are how much speed improvement can you get, and how little loss in accuracy can you get, and how aggressive should the beam be. And let me talk about our approach in more detail. So here's the CKY star chart, and each cell in this chart corresponds to subsequence in the sentence of the sentence. So for example, the cell 2,4 corresponds to the subsequence lice biting his nail. And each circle here corresponds to constituent in cell. And usually the constituents are combined from two constituents in the lower cells. And here's the circles here. So look at the cell 2,4. And those two constituents have score. The parser estimates the score for each constituent, and the score is log probability of each constituent. And it is in log scale, and they are not normalized, so they have positive numbers. So let's say the green dots here are part of final analysis in gold oracle, and the red dots are not. So in this case, the red dots have more score, which means at this point, at the cell 2,4, it seems more probable than the green dots in the gold standard oracle. But actually, what you want to get is the green dots here. So you measure the gap, which we call beam ratio here. So it has now minus 1.9 gap here, which means if we apply beam less than this minus 1 point gap, it will eliminate the red dots here. So we cannot get the gold standard oracle finally. So the important thing is here we calculate the beam scores during building the chart. Currently, the original parser does not estimate scores before during building the chart. It builds the chart, then to find the best final analysis, it estimates scores for only those constituents that are part of the final analysis. So it could hurt speed for instance. So to see how aggressive the beam should be, we measure this beam ratio for Wall Street Journal Section 0 data. So here's the result. The x-axis is the span, and the y-axis is the beam ratio in log scale. And the red dots here, the constituents in the chart, and the green dots here are the constituents that end up being in the gold standard oracle. So they are what we want to get finally. So there are so many red dots here. So what we want to do is to eliminate as many red dots here without eliminating many green dots. So how we do? So and what you can see here now is that it's much denser for shorter spans on the left side. So the beam approach might be more effective for shorter spans, intuitively. So we can apply fixed beam value, which means we we draw a line and cut off all constituents under that beam ratio. So in this case, we apply the beam ratio of 0.05, and it's about -5 in log scale. So hence the graph. And we could apply beam search only for shorter spans, as you can see here. And you might get a wrong impression from this graph, because actually the red dots on the right part are eliminated because many of them are combined from the red dots on the left, which are eliminated. So, and I'll talk about why we did in a moment. So the problem is, where is the sweet spot for test data? Is a sweet spot for Wikipedia data the same as the sweet spot for Wall Street Journal data, and so on. So we can apply various fixed beams width, and we can set various beam threshold.
Let me ask you a quick question.
Mm-hmm.
So when you draw, let's say, one of the blue lines, let's say the top blue line,
Mm-hmm.
the 0.01 beam, right? You could have redrawn this plot by saying all constituents of size, let's say, I don't know, 2 or 3 below the beam of 0.01. If you eliminate those, then you can find out in the cells with larger span what the distribution of red and green dots is.
That's right.
Does it look very different, or does it look about the same?
Uh-huh. Actually, I didn't plot the graph, but yeah.
Because you did say that a lot of the red dots will go away because they are made of other red dots on the left, which you remove.
Yeah.
But I'm worried that maybe some of the green ones will also go away because you eliminated some of the green ones on the left.
Mm-hmm.
The question is, where do you do more damage?
But yes, you're right. I agree that. But we can see the result from, we can see the effect from the result.
Just another quick question. Why draw a horizontal line? Like, why not just make it depend on the length?
Yeah, actually, it's a good question. Actually, we try variable beam value. We draw curve, and we draw linear line. We fit the curve for data, but fixed beam value actually worked quite well than the other variable beam values. So I only present the fixed beam value in this talk. Any other questions here? Okay. So this is the test result on Wall Street Journal section 0. So as you can see, with beam search applied, there are much gain in speed, and there is some loss in accuracy for beam value of 0.01. But surprisingly, there is also a gain in accuracy for some beam values. I explained that in a moment. We picked the beam value of 0.05 here to test various beam thresholds, and this is the result. So so we were able to get better performance when we apply beam only for spans of 40 or less of length. And we could gain accuracy too. So the factors that affect speed is the what I already told about in the previous slides. So the beam search may or may not increase speed, but it actually could gain quite big improvement in speed. And here's the analysis on accuracy. Accuracy does not necessarily decrease with beam search because the constituents that get larger score estimates from the parse model does not necessarily are not necessarily the same one in the gold standard article. And the beam search makes the chart size smaller, and it allows the parser to parse more sentences, so it can actually improve accuracy too. But it is true that accuracy tends to decrease with more aggressive beam. So we tested this beam search approach to various data sets, namely on Wall Street Journal Section 0 and 221 and 23. And we applied to Wikipedia 300 sentences data set. So these are all annotated, so we got accuracy results here for those 4 data sets. So as you can see, it could even get 126% for Wikipedia data sets, and it could get accuracy improvement in Wikipedia data too. And for 2,500 Wikipedia sentences, we didn't have annotations for that, so we only measured the speed gains here. So the conclusion is fixed beam search actually worked. Fixed beam search gained 77 to 126% speed improvement with a little loss of accuracy, and sometimes with accuracy gain. And the sweet spot for Wall Street Journal is actually compatible with Wikipedia data. The same setting worked for both data sets. So we are still to integrate this approach with other approaches that Yue and Tim tried during the workshop. And we need to apply this beam search method to larger Wikipedia data sets. And I'll stop here and I'll hand over to Yue. Thanks.
You plotted a two-dimensional scatter plot of red and green, where the only features you were looking at to try to help distinguish red from green, without knowing the oracle, were the gap and the sentence length. Are there other features that you might consider that could help prove?
For beam search?
Yes.
I'm not sure about the other. Yes. Yes, we can estimate the outside scores for various constituents and take that into consideration to eliminate some constituents. And yes. It's okay? Thanks.
So, good morning. I'm Yue Zhang from Oxford. I'm going to talk about child cell pruning. So, while beam search can be seen as a method to prune low probability constituents from each child cell, I'm going to focus on pruning whole child cells in this talk. And in particular, our approach is a tagging approach. So, the idea is that before parsing, we take a separate step to assign tags to each input word that indicates whether or not it can begin or end a multi-word constituent. So 2 types of tags are assigned to each word to indicate the begin and end properties. And these 2 kinds of tags are assigned independently of each other. In each case, a tag takes a binary value. During parsing, this kind of tags are used to prune the parser chart. And the method has been applied to CKY parsing in context-free grammar. Suppose that the input sentence contains 5 words, and this is an illustration of our parser chart. We call each horizontal line a row and each vertical line a column. Each row contains constituent that has the same size, and each column contains constituent that starts from the same word. And therefore, each cell in the chart contains all different kinds of constituent that covers the same input words. For example, cell 2-3 in this chart contains all constituent that covers the words like playing cards. We're not concerned with the first row, which corresponds to single word constituents, because if we prune any cell in the first row, we can't construct a parse. This is the pruning effect of begin tags. In this example, the gold standard begin tag for the fourth word is 0, which means that it can't start a multi-word constituent. In this chart, it means that none of the cells in the fourth column can contain any constituent, and therefore the pruning effect of a begin tag being 0 is to cross out a whole column. This is the pruning effect of AND tags. The gold standard AND tag of the third word is 0 in this example, which means it can't end a multi-word constituent. In particular, it can't end the constituent that starts from the second word with size 2, or the constituent that starts from the first word with size 3. And therefore, the pruning effect of an AND tag being 0 is to cross out a diagonal.
Excuse me, I don't understand why you can't say we like playing.
We can't say?
We like playing. In other words, playing can be the end.
But not in this example. So it's the gold standard derivation.
Yeah, I'm just using
I
the...
thought that this is a universal or something. No.
Oh, no. This is applied to a chart, particular parse chart. Yep.
All right.
And so we can combine the pruning effect of begin and end tags to form the final pruning. That is how we can apply the tags to prune the chart. Now, this kind of tags can be derived from a maximum entropy model. We use a quite standard trigram tagger to assign these tags, where features are extracted from type trigrams, as well as 5-word window with the current word in the middle. The tagging accuracy is around 96% for both begin and end tags. There are two ways to train the tagger. One is gold training, where we derive the training data from gold standard parse trees. The second is cell training, where we derive the training data from parser output itself. Here are some development tests using CCG bank data. We train on Wall Street Journal 2-21 and test on Wall Street Journal 0. We can see that when we apply only begin or end tags, we both observe speed improvement with a little bit accuracy loss. And when we combine the two kind of tags, we get more speed improvement. The last two rows in this table shows the gold oracle and self oracle, which are the best we can get from these two kind of training method. For gold oracle, we basically, instead of using the tagger, we derive the begin and end tags from the gold standard parse tree and use this to prune the chart. And for self oracle, we just derive the tags from parser output and then use this tag to prune the chart. Now we've applied an existing method to CCG parsing. We further developed this method to increase its pruning power. And recall that the pruning effect of a begin tag being 0 is to cross out the whole column. And because begin tag takes a binary value, we can either cross out all cells in a column or no cell at all. So in this particular example, we can't cross out the second column because the second word starts a 2-word constituent, card games. In order to increase the pruning power, we can change the binary value into a discrete number that indicates we can actually prune the column from a particular level. In this case, we can prune from third level above. And we call this kind of method level tagging. End tags can also be used in a similar fashion as the begin tags. And in this case, the end tag prunes from the second level above. And that is equivalent to a binary tag value being 0. The pruning effect of binary tag in this example is to cross out a column plus a diagonal. While the pruning effect of level tags in this example is to prune besides the column and diagonal, also part of another column, and therefore the pruning power is increased. A summary pruning tag, we have a set of n tags where tag 0 means no pruning, and tag n means that we prune from the n+1 level upward. We fix this n in order to have a fixed set of tags. Now, the level tags are derived by training a maximum entropy tagger for max span tags. A max span tag takes the same value as a level tag. However, its meaning is different. It represents the size of the largest constituent a word can start or end. Max span tags can be read off parse trees directly, simply by reading the largest constituents, and therefore training data can be prepared for the max span tagging, and then a maximum entropy tagger, trigram tagger is trained. During decoding, we just compute the forward-backward probabilities for max span tags and derive the level tags from these probabilities. And here's an example. Suppose we want to assign the level tag, begin tag, for the second word in the sentence. And the probabilities of max span tags being 1, 2, 3, 4 are given in cells 2, 1, 2, 2, 2, 3, and 2, 4, respectively. And the probability of level tags can be computed by summing up the probability of max span tags in the bottom-up direction. Just for example, the probability of level tag being 1 is just the probability of max span tag being 1, which is 0.1. But the probability of level tag being 2 is the sum of probability of max span 1 and 2, 0.8. And similarly, level tag 3, 0.9, and 4, 0.9. The theory behind this has been reported in the previous progress report, and I don't have time to go into details. As we move upward the column, we see that the probability of level tags increase. So we can set a threshold value, probability, and choose the level tag as the smallest non-zero value that has the probability above this threshold. For example, if our threshold is 0.8, we choose the level tag 2 and prune from the third level. And if the threshold is 0.9, we choose the level tag 3 and prune from the fourth level. So this threshold is basically a trade-off between accuracy and pruning power. The idea is that when we're not sure enough, we can prune the cell, we just don't prune it. And the end level tag can be assigned similarly to begin level tags. Here are some development tests on CCG bank data, where we compare the effect of binary tagging and level tagging with a tag set containing 3 tags, and level tagging with a tag set containing 5 tags. By comparing binary and level tag 2, we can find that the cell oracle is much better for level tagging, which shows that we can do much better with level tagging. And by comparing the second and third row to the last row, we find that the 5 tag set achieves much better pruning effect than the previous ones. And therefore, we set the tag set to n equals 4. And lastly, I'm going to show some final test results on Wikipedia data. We did this experiment by training the parser using Wall Street Journal data 2-21 and used the parser to parse the whole Wikipedia. Then we choose some of the parser output as the training data for the binary or level taggers. And we use 2 different sets of test sets. The firstly contains a small amount of manually annotated data so that we can have an idea about accuracy changes. And secondly, we use a comparatively large amount of raw data just to measure the speed up. This is the results for the first set, where we find that using both binary and level tags, we can achieve speed improvement with a little bit loss of accuracy. Using this set of data, we're mainly concerned that we don't lose a lot of accuracy. And this is not a very good indication of the speed up we have simply because of the small amount of data. Now, secondly, we use this set of data to measure the speed up. We find that, again, using both binary and level tags, we can achieve a fair amount of speed up. And using level tags, we can generally perform better than using binary tags. However, when we increase the number of training sentences from 40,000 to 1 million sentences training data, we didn't find a large amount of speed improvement. In other words, it doesn't scale up very well in the self-training case. In this particular case, we can only say. So as a conclusion, we find that the tagging method is an effective method to prune the chart. And level tagging generally does better than binary tagging. We also found that a positive result is that self-training is effective. We achieved more than twice speed up, from 47 sentences per second to over 100 sentences per second, with a little bit accuracy loss. However, a negative result is that we didn't find consistent improvement when we scale up the size of the training data. But we hope to do more study about this later. So I'll hand over to Tim.
Yeah, so on these speed up kinds of things, I gather that this is an embarrassingly parallel problem. That is, if I have lots and lots of sentences and lots of machines, I can just send out the sentences to different machines.
Yep. Yep.
What kind of machines do I need to do this? Can I do this on very minimal machines?
Actually, the tagging phrase can be achieved using one machine only. But the training, you mean the training because the...
I'm asking what kinds, not all machines are equal. Like, do I need a lot of resources of any kind, memory disk?
No.
Not really.
So very modest machines would do fine on this.
Yes, actually it depends on the implementation of the
So I'm sort of
tagging
wondering
model.
what kinds of speeds would be good enough? I mean, is 100 sentences per second on something that's smaller than a cell phone perfectly adequate?
I guess it really depends on the demand, right? Okay.
Suffice to say, we're not at 100 sentences a second on a cell phone. But if cell phones keep getting more powerful,
Well, I'm asking here, what do you need?
yeah.
Do you need more than a cell phone? What's in here that really that's hard?
Well, the memory footprint, what is it?
It's RAM.
Yeah,
So how much
few
memory?
hundred megabytes.
I can't hear.
300 megabytes, for example.
Yeah, it's closer to a gig.
And how much of that is just the lexicon?
No, it's
Almost
not.
none of it. It's almost entirely the fact that we're building all possible derivations except for when we're doing pruning, which is like, anyway, well, I'll be talking
It
about
seems like excessive amount of memory.
Okay.
Okay, so my name's Tim Dorborn from the University of Sydney, and I'm talking about the project that I was working on, which was 1 parse per n-gram. And this was an exploration of the idea that we assert that there can only be one possible derivation for particular n-grams. So that if we know that some n-gram always has one particular derivation, why bother parsing that particular n-gram if we always know what it's going to be? And so a good initial statistic to calculate to see how well this idea might progress is how many n-grams which form constituents in the parse chart actually have this one unique analysis property that we desire. And so looking at Wall Street Journal 2 to 21, for different n sizes in the n-grams, we can see that the uniqueness factor for derivations is quite high, with up to 5 grams being 99%. Yep.
Is that because most of the 5 grams only occurred once?
Yes. Obviously, as you go down, the frequency decreases, but yeah.
But the statistic says when a 5 gram constitutes a constituent, then it has only one analysis. It doesn't mean that if you find this 5 grams somewhere in the wild, that it will be a constituent and will have that analysis.
Well, yeah, this is just within 2 to 21.
So if you're parsing, you don't know that at
Yeah.
the beginning.
Yeah.
You don't know that it's going to be a constituent.
Yeah.
Yeah, it might be more meaningful to ask something like, if you see a 5 gram and the 5 gram has occurred before, what are the how well would you do if you gave it the majority parse from the 5
Yep.
terms you've had
Would-
before, not necessarily requiring that it be a constituent, so you just assign
Which
some
is
structure with
somewhat what we
constituent.
do, but we'll get to that. And these are reasonably promising statistics, considering the size of 2 to 21 in the Wall Street Journal as a corpus. And so, yep,
What was the training data for the parsing on 0 to 21?
the training data was Wall Street Journal.
The same.
Yep.
But he's not parsing anything.
I'm not parsing any.
Statistics based on the trees.
So what do you mean by unique?
So the derivation within the parse tree is the same
I see. Okay.
for all occurrences of that n-gram. If that n-gram forms a constituent.
Only for that span,
Yeah, only for that span, assuming it conforms a constituent. Forms a constituent. And so the overall structure of how we do this one parse per n-gram is that we parse some corpus of text, be it the Wall Street Journal or Wikipedia, and we then perform some frequency analysis on these chart structures to determine which constituent forming n-grams are the most frequent. And we do this by doing a rank set of counts, rank counts and 2 sets of frequency cutoffs. And so by doing this, we hope to eliminate n-grams which appear only once, like really low probability, so we don't get noise in our databases. The next step, once we have the n-grams that we desire and their associated representation, we do binary serialization so we can use them later on. To do this, we use quite low-level techniques such as pointer swizzling and clever uses of hash functions, fixed-length databases, and caches to gain maximum throughput. So the overall aim of this is to go really fast, if possible. So we don't want to have to parse the n-gram, so we want to save as much time as possible.
I'm just curious what pointer swizzling is.
Okay. So pointer swizzling is the phrase where, so you have some, take the C or C++ for example, so you have some pointer to some struct, and in it has pointers to other things. You want to be able to take that initial object and write it to disk, such that you can load it back in at some other point in time and have all its dependencies still work. And so you have to follow those pointers and do some offset calculations and things and write them to disk in turn, so that when you get them back out of disk, you can update those pointer locations to some new location and everything will still work. So it's akin to kind of memory management style things. So quite low level.
Like a linker.
Pardon?
Like a linker.
Yeah.
To close the program.
Yeah. Oh, yeah, and the database we use for this is called Tokyo Cabinet. It's an open source database on SourceForge. And so pictorially, what the overall system looks like. Say we see the n-gram BCD. We see it lots of times, and we're going to make the assertion that this one particular derivation for BCD will always be that derivation. So we have our chart structure for BCD, we use our pointer swizzling and our serialization, and we dump it to the database. At some later point in time, when we see the sentence A, B, C, D, E, we say, okay, we don't want to bother parsing BCD because we assert that it's only one possible derivation. So we grab from the database this initial structure, plonk it in, and we block out all the cells below it. We totally count them out of the chart. They're all gone.
This is lexical, right?
Yeah, lexical only for the minute. And so what we do by doing this, we limit the number of possible combinations that can happen within the chart. So these cells can't be used by any form of combination. And so our initial experiment was to have a go at Wall Street Journal again, using these n-gram databases. And so we trained on 2 to 21 and evaluated on 0, 0. The baseline F-score for the parser, when you run it over 0, 0, without any of these n-gram constraints, is that you get a F-score of 85.51%. Now, when we applied varying n-gram database sizes to section 0, 0, these databases that we've constructed from 2 to 21, we get these F-scores. So just a little bit less than the baseline, which is somewhat not unexpected to go less. I mean, for the S-score to decrease, considering the size of the Wall Street Journal. So what this probably means is that the frequencies that we trained on were not enough to get reliable statistics, so that one particular n-gram would always be the particular pars we're after.
Usually each line, each row of this table says that corresponds to only that order n?
Yep, only that order n-gram.
Not all of the previous one.
Correct, just that order. Now, if the parser could, once we apply these particular n-gram database constraints to a sentence, if the parser cannot form a spanning analysis on its first attempt when we're using these n-gram, pre-parsed n-grams, we let the parser back off, take off the constraints and have its normal attempt at the sentence again. And so we'd also like to know then how many sentences reject these constraints. The parser cannot form a spanning analysis when we put on the varying n size constraints. And that's what this table shows. So for Wall Street Journal section 0, we attempted to use bigram constraints on 1,023 sentences. 208 rejected them in their first attempt, which is 12%. And so these percentages are quite high. And the real downside of these high percentages of rejections is that we lose all speed benefit that we had. So the speed benefit we gain from not having to parse these structures, we lose almost entirely because we have to retry 12% of the sentences twice. Like we try them first with the constraints, they fail to parse, so we take off the constraints and parse the sentence again. And it ends up that the speed is almost identical at the end of this as if we never started the process in the first place. And this is for a number of reasons. One particular reason I'll quickly explain now. Consider the sentence, I saw the Christmas tree, in its CCG analysis. And say we remembered the bigram Christmas tree in the context of this sentence. So we remembered that chart structure for Christmas tree, and Christmas tree forms a noun. And then at some later point in time, we come to parse the phrase Christmas tree lights, which has that CCG derivation at the top, which is one big noun phrase, one big noun. If we try and use the bigram that we learnt in the previous context where Christmas tree is a noun, so we applied the constraint, we put Christmas tree as a noun, light still gets the category noun, we're unable to form a spanning analysis. And this happens, this situation accounts for quite a high number of these percentages here. So, future work for this project. We need to address this previous situation with the Christmas tree lights. We need to train on a larger corpus such as Wikipedia. Unfortunately, we didn't get to finish this implementation until quite late in the workshop, so we didn't get time to run any big experiments, anything bigger than the Wall Street Journal. We need to investigate some better back-off strategies, so what happens when the parser fails to parse with the first set of constraints, because currently we just throw them all out and try again from scratch. We need to investigate using more context than just the lexicon, so using pos tags, for example. There are a number of other implementation tricks we can use that we know about already to help speed it up. And just as a side note, I'm working on this project until the end of November as part of my undergraduate degree back in Australia, which I finish at the end of this year. So this is really not the end of the story just yet. In conclusion, we managed to implement this idea during the course of the workshop. There was not enough time to perform suitable number of experiments to determine whether this strategy will work or not work. The initial results were not too promising, but it's still early days yet.
So it looks to me like you should recast this as a super tagging project. Let me explain what I mean. So what you're essentially doing is the way the original super tags were obtained, you push the context-free structure all the way down onto the individual words to get your lexical entries. What you're now saying is, let's stop somewhere in the middle And that's sort of the lexical entry for this multi-word phrase.
Yep.
So what you do is you extract all multi-word phrases of length 1, 2, 3, 4 up to max sentence length from your Wall Street Journal corpus.
Yep.
And now you've got yourself this gigantic lexicon where there are multi-word spans with a single CCG tag on top of them.
Yep.
Of course, there's an assumption that the analysis underneath is somehow known.
Yep.
And now you can take tons and tons of unparsed text, do the full CCG parsing using only the single word lexicon, get the full tree, and then ask yourself, what were the multi-word expressions, what tag did you
Yep.
get at the top level? And you can then start training, saying, make sure, when you see this multi-word span, this super tag for the multi-word span is okay, and that anything on the smaller things which would have led to other multi-word tags are not.
Yep.
And so basically you've got yourself a free training and test setup.
Yep.
And,
Yep.
and this way what you do is you do this thing at the super tagging level, where as you process the words, you take a multi-word expression, go to super tag and move on. And from the way you described, or maybe somebody else did, for that you can get unlimited again.
Yep. So we have had that idea, and that will happen probably sometime later in this year.
Between now and then.
And that also is somewhat related to why this example fails with the Christmas tree lights, is that because there's no interaction between my stuff and the super tagger, when you see Christmas tree lights, it still gets the initial set of CCG categories. So this is why lights gets the category M, it doesn't know anything about this, which is why we fail to form a span. Conclusion?
Can we move on to the conclusion?
There's questions
We've
afterwards.
got one more session.
Yeah.
Okay, so my name's James Curran, and with Steve I was leading this project. So now you've kind of seen all of the components of the system. So I'm going to attempt to summarize in hopefully a small number of minutes, so we've got some time for questions, all of the things we feel we've learned or produced over the last 6 weeks. But before I get into that, I wanted to actually just do a few of the thank yous so that I could end on our big final numbers slide and not have these getting in the way. So first of all, I'd just like to say to all of the JHU people here that this was a pretty amazing experience, and so thank you very much for the opportunity. Particular thanks to Sanjeev, who's been our kind of food person and everything else, and kind of coming along and checking out how we're going and showing us Baltimore, so that's been absolutely fantastic. Also a big thank you to all of the JHU admin and support team. If I could find some way of stuffing Desiree into my suitcase so I had an admin person like her back in Sydney, then I think I'd do that. So it's really been a fantastic environment. There are a few people we didn't actually bring with us that I thought I should quickly mention here as well. So Steve's postdoc Laura in Oxford has been doing a lot of annotation work, and as Steve mentioned before, one of my PhD students, Matthew Honnable, also helped us out with some annotation work. And we really should acknowledge both Julia Hockenmeyer and Mark Steedman's work in this whole entire research agenda that we've been working on. So without Julia's massive effort to create CCG Bank, then there would be no parser because there would be no training data. So that's been huge. And of course, having Mark work with us on the whole underlying formalism and connecting it with the parser and things has been great. And the final person I want to mention is Greg Ryan, who's a system administrator in Sydney, who's been keeping alive a very large number of machines for us while we run these experiments. Okay, so now I want to move on to the things that I think are the kind of deliverables from the project. So the first one, as Steve mentioned at the beginning, is a new release of the CNC tools that will probably come out sometime within a couple of weeks after the workshop. So basically we had 7 development branches all running in parallel, and it will just take some time for us to actually merge all of those development branches back together. I've done a bit of merging already, and we have a surprise number at the end that even the rest of the team hasn't seen yet as how fast the parser goes, so a bit of fun for everyone there. So also we have Kurt's great work on the tokenizer and sentence boundary detector, so all of that stuff will be integrated into the next release of the parser. and also Jesse and Jonathan's work on the MPI implementation of the Maxent estimation code, so that you can, if you've got yourself, like we do, tens or hundreds of millions of words of training data for a pos tag or a super tag or anything like that, then we have the necessary software for you to handle that. And as I said, we've already experimented with this up to a scale of somewhere a bit greater than 1 million sentences, which is a pretty enormous training set. Along the way, we've also developed a fully parsed copy of Wikipedia in a number of output formats. And one of the things that we've done now, and I'll talk about this in a minute, and it's kind of a bit of an answer to Ken's question to some extent. At the beginning of the workshop, using the machines we had, and I'll talk about that in a minute, we could parse Wikipedia in about 5.5 hours. So around 1 billion words in 5.5 hours. Now, well, I'll save the number till later, but now we can do it a whole lot faster. And I think the other thing that we've kind of demonstrated, which is a bit of a funny thing, is if you're in a university environment like us, where you don't have enormous Google-esque resources where you can call up 100,000 machines, what can you do if you actually want to run some of these large-scale experiments? Well, it turns out that if your students are away, then stealing undergraduate labs, even though they've only typically got 100 megabit internet connections, Ethernet, you can actually get a hell of a long way just using labs of computers to do this kind of stuff. So all of the experiments that the students have talked about are entirely run on commodity, and when I say commodity, really quite low-level commodity desktop machines that you'd put in an undergraduate lab. Okay, so they're the kind of deliverables to some extent. What are some of the research questions we've asked, and what are the answers that we've come up with so far? And this is just a quick fire set. So first of all, we had this grand idea at the beginning of whether we could integrate tokenization with document processing. So could we recognize HTML tags in exactly the same process as the tokenization, and could we do that in some kind of dynamic way using regular expression libraries? Unfortunately, the answer is no, and Kurt really bashed up against this as hard as possible to make all of the regex libraries that seemed suitable to do this for us, but it just turns out the technology's not quite there yet. Can we speed up the parser with super tag or self-training? Well, the answer to that one is yes, definitely. And really this comes down to the idea of that we can predict what the parser is going to do anyway, and I'll come back to this in a minute. And also putting in some larger feature contexts helps a little bit too. Can we speed up the parser with an adaptive beam search? Well, this is an interesting one because actually we had a beam implemented. In fact, the beam is about 5 years old, which means that the bug that's in there is also 5 years old. So Byung-Gyu did some fantastic work to actually uncover something that in part meant that we thought the beam didn't work, but it did, and then he did some more great work on this idea of the adaptive beam too. So yes, the beam works for us. Can we speed up with cell pruning using a tagger? Well, you saw the numbers for that just before. So, and that's particularly true if you're going to use this level tagging. And the final thing in our list of research questions is if we've got a bunch of richer features, for example, information from lexical semantics, distributional similarity, and so on, can we do a better job of coordination than the parser currently does? And the answer to that is yes, definitely as well. So they're the main set of research answers, I guess. And that then leaves us with things that are still in the yet to be decided bag. And the first one of those is what Tim just talked about before. Can we use pre-parsed n-grams in some kind of efficient way to either speed up the parser or potentially get some kind of accuracy gain over a really large collection? And I think the big issue here is, of course, that there is still some ambiguity in these n-grams and how that's actually going to be dealt with. And I think the other thing that Tim didn't really point out is pointer swizzling isn't just a cool term, but it's actually something that's bloody hard to implement. So, you know, he spent 3.5 days with one particular bug that involves stamping random bits of memory with random bytes. You know, these kind of things are typically the kind of thing that, you know, a Java virtual machine is doing under deep in its internals, and most programmers don't have to worry about it. But the reason we have to is that the parser is actually already incredibly fast at bashing together bits of categories, and so you really need to have something like what he's trying to implement to get the speed gains we hope to gain. And then the final thing, of course, our really blue sky proposal was, can we exploit fact redundancy on web data to create new annotated or partially annotated training data? And I think that this one still really is an enormous maybe. I personally feel like we've got a long way further forward on this front now. We understand a lot more about the problem. And starting to use Freebase that has all of these facts already expressed in a way that we can access rather than having to identify them first is a major step forward. And this is something that we'll definitely be carrying on with over the next however long it takes to decide it's not a good idea or it's a brilliant idea. Okay, so I just wanted to have one slide that kind of summarizes, I think, the key idea or ideas from this project. And really, efficiency has become our primary obsession to some extent because we want to have a parser that people can actually use. And really, efficiency has turned out to, all of these different types of efficiency you can think of in terms of keeping the chart cells, so the individual cells in the chart, as small as possible. So have as few categories in there that they're constructing things with. And if you think about all of the different things we've talked about in this context, it actually fits in quite nicely. That first of all, we've tried to set up the super tag as such that it predicts not only the gold standard, but actually something a little more subtle than that, and it's to predict what the parser was already going to do anyway, right? Because there's almost no point in giving the parser tags that it's then going to ignore, even if they are the gold standard tags. So you might as well give it what it's going to use anyhow. And so this allows you to, at the super tagging level, insert fewer things into the chart. Then if you think about Byung-Gyu's work on the beam search, well, this is exactly the same idea, where he was actually measuring, well, what categories does the parser actually choose at a particular level, and what are the ones we can throw away? So rather than inserting fewer, it's the process of just removing more at some later stage in the processing. The next level up of that in terms of aggression is to say, well, not only do we want to eliminate some of the categories from within a particular cell, we actually want to throw a whole cell away entirely, which is what Yue was working on. And this is, again, basically similar to the idea of saying, well, what are the cells that the parser is actually going to choose and what cells is it going to ignore entirely? And that then brings us to the final level, which is what Tim was working on, which is to say, well, can we take a whole bunch of cells and throw them away en masse by identifying a larger constituent and throwing it straight into the parser? So I feel like most of the strategies we've employed are actually at various levels on that scheme of throwing away more and more of the chart on the basis of local information. Now, the thing that's interesting about this is most of these techniques here are not using very complex information. So the super tagger is only looking at the local context. The chart labeling was just exactly the same features as the super tagger uses. The n-grams was only looking at the words themselves, right? So we're getting quite a lot in terms of things we can throw away using fairly simple information. Okay, so what I wanted to just quickly show you now, in fact, maybe what I'll do is I'll do the last couple of slides, and then if people have got questions, I'll run the parser in the background. It's not overly exciting except to us when we see the number of sentences flying by, but it is quite cool. So what I want to do is just summarize with our kind of final number set, and I can see the team getting very tense over here. So this was the pre-JHU workshop set of numbers. And these, remember, these Wiki 300 numbers are based on data that Steve annotated during the course of the workshop. I'm then going to report a few of the numbers for the cell pruning and also the beam search, which we haven't integrated back into the full parser yet. And I've put here approximates on these because these numbers weren't actually run on the same machine, so I've kind of normalized so that the accuracy figures are right. I've also put stars here on the cell pruning because on the Wiki 300 data, UA got only kind of 1.4 multiplier of improvement in speed, but actually when he ran it on the final 2,500 sentences, it was up around a factor of 2. So it's being a little unfair to that. Now, there are a bunch of code fixes that we haven't talked about that are kind of pending things that when you get to come away to Baltimore for a few weeks and actually fix, we got to fix. So that got us quite a bit of an improvement already in terms of the speed on both the Wall Street Journal and on the Wiki 300. And we also got a little bit, although not particularly interesting, improvement in F-score as well. Then if we add in the 400,000 sentences of the supertagger model using the Maxent BFGS implementation, and so this is the kind of large-scale stuff that Jonathan and Jesse were working on. You can see that the speed goes up quite a bit here, and goes up to a lesser extent for the Wiki 300. And our final number, if you throw in all of the longer features that Jesse and Jono worked on as well, you can see that we managed to get quite a whopping factor of 3.3 increase in speed over the original model. So you can either take 1/3 as long to actually run the parser, or you can buy 1/3 of as many machines as you were going to if you were Google and deciding to parse all of the web. And I'm pretty sure that these things, because they're actually quite orthogonal ways of affecting the number of cells, those multipliers will come in here. My guess on the basis of things we've done in the past would be that we end up with a factor of 5 increase overall, which I was hoping we'd be able to get to an increase of 2. I thought a factor of 2 would be a pretty good outcome, and so to get a factor of 5 is pretty amazing. So that just leaves me to do one final thing, which is to say on behalf of Steve and myself that it's been great fun working with the team. A bit of absolutely everyone's work has ended up in the final version of all of these numbers here. It has been a really great team effort, so thanks very much.
As we all know, the best parser in the universe is by Charlie. And I would like to know how it compares with your parser when we disregard the speed.
So you want to know the accuracy comparison?
Yes.
So comparing parsers fairly that produce...
So while Steve does that, I'm just going to start the parser running so that you can actually see.
Big Fred's looking for trouble.
So comparing parsers fairly that use different representations is very difficult. So of course, because the Charlie App parser is based on the Penn Tree Bank, that's the standard parsing task, it's very easy to compare that with the Collins parser and the Berkeley parser because they're all playing the same game. We're playing a slightly different game, we've got slightly different motivations. Having said that, we did some work recently to make the CCG parser produce Penn Tree Bank structures, even though that's not really what we're interested in, but because we keep getting this question, and we did it. And we got results that were comparable with the Berkeley parser. So we're comparable with a state-of-the-art Penn Tree Bank parser producing Penn Tree Bank trees, even though that's not what we're interested in.
How do you compare with the Berkeley parser on Wikipedia? I mean, that's quite an interesting question, I think.
But see, the problem is that we've got our test set that's grammatical relation. So how do we get the Berkeley parser to produce those GRs?
To tell the truth, the real question that the real comparison that I'd like to see, and I may be different from other people, if you're looking for additional comparisons to do, would be to compare with MST parser and mult parser on unlabeled dependencies. It seems like that would be a fair comparison, since I believe they're also looking for long-distance dependencies.
Yeah, but I still think there would still be this mapping problem, even then. So to get us to produce unlabeled dependencies that are exactly like the ones in the test set would still be quite difficult.
Yeah, so there have been a couple of papers lately, actually, David Smith and I have one coming in MLP, and we're not the only ones who have done this, about adapting cross-annotation standards, for example, for dependencies. So you could allow yourself, a small adaptation set to go to the other style, like if conjunctions are handled differently, that kind of thing.
So I think that the short answer is it's very hard to compare parsers across different formats.
Well, can you say if you disregarded speed, what the results would be?
Oh, okay. So I guess at producing Penn Tree Bank trees, the Charlie App parser is slightly better. If you're interested in doing something like recurring unbounded dependencies, it's not at all clear how the Charlie App parser compares then. So I've recently done an evaluation on that where we created 700 new test sentences with unbounded dependencies marked in them. And we compared with things like the Stanford parser, the Tokyo parser, and the Tokyo parser and the CNC parser got about 50% overall. It's very poor at unbounded dependencies, but much better than, say, the Stanford parser, which was about 40, and the Cambridge RAS parser that was about 25. So we'd like to try and move away from the Penn Tree Bank, which is what we've been doing here, and try and get an evaluation scheme that everyone's happy with, not Penn Tree Bank trees, so we can do a fair comparison, and then I could answer your question.
But The last question was a little different. The last
Yeah.
question was that if you employ your best techniques
Right.
for accuracy and completely forget any shortcuts, how much do you gain? In other words, how much are you giving up because of your speed ambition?
Almost
Oh,
nothing.
none, no.
Yeah. In fact, sometimes some of our speed ambition has resulted in accuracy improvement. So we're really not cheating ourselves or anyone else when we're doing this evaluation. It's literally, this is kind of the native speed of the parser and its native accuracy in a sense. There's a little bit we can do. You know, we can, for example, get our coverage up to 100% by allowing the charts to be absolutely enormous and things like that. But we're already up over 99%, which is, you know, beyond where most of the parsers that don't do some kind of robustness check work. So I don't think there's actually much to change on that particular front.
So just to go back to the conversation Steve and I were having a moment ago. Steve, if you wanted to...
Not directed to James?
James is what...
I think I heard the conversation. I might be able to help.
Yeah, right. If you wanted to compare to something like MST parser or mult parser, a way to do it fairly with the same annotation standards would be as follows. Take your parsed Wikipedia and use that as the sole training data for both parsers. Then they agree on annotation standards. It's true that you'd be training the pure dependency parser entirely on unlabeled or labeled dependencies. You'd be training your parser on, it would be getting more information because it would also see the CCG tags. But at least you'd be able to compare the output fairly on accuracy. If you do better, then somebody might ask, well, how hard would it be to get that richer training data for a new language? But at least for English, you'd be able to do fair comparison on speed and accuracy. I think it would be very worthwhile. Since you keep getting comparison, in this comparison question, that might be one which is easy and fair to do.
Yeah, well, I think so. The problem is that the kinds we've done so far are very labor intensive. That's the problem. So converting back to the pen tree bank is just a complete dog of a task that you wouldn't want to set anybody on, really. And also, people haven't been overly convinced by it either. So when you get low translation scores across to the other scheme, and even your upper bound is very low, people that haven't tried to do that conversion ask why. But as soon as you've tried to do it, you don't ask why anymore. Because there are just loads of edge cases.
Yeah, so I don't see the same complaint about what I just suggested.
No,
We can take
no.
it offline.
So I've got another learning evaluation question, and that's why not circumvent this discussion by having a task-based evaluation where you actually use the parsers for something?
So the problem with those is that most applications that in some sense really use the parser, right, or really use parsers, are fairly heavily tuned to the particular parser they use. So, for example, in our question answering system, substituting in somebody else's parser would be an enormous bit of work to do. And most of the time, if you're a QA person, for example, you're not really interested in doing that parser evaluation. But actually, it really is, I think, exactly the thing that we have to do. But again, it's another labor-intensive thing, I think.
Although, just to give a slightly different answer to that, one problem you've got, of course, is that we're not yet in a position where parsers really help with a lot of applications, which is the point I made at the beginning. So I've seen one evaluation like that, and you're talking about a difference of a few percent. So it was some event extraction task that Tokyo guys did. They were getting 50-odd%, and you tweak the parser a bit and you get an extra percent or so. Well, I'm not sure how interesting that is either. So we need to get to a point where we can demonstrate that these parsers are really useful in applications, and that would be the perfect evaluation.
Do you need higher accuracy before they are useful, or just they're not useful in general?
Well, I don't know. I mean, so as I said at the beginning, one thing we want to do is give people the tools to start answering that sort of question using these things.
And there's been a lot of kind of what you could call data one-upmanship, right? So there are lots of results where I think if you say, if you're only allowed 10 million words and you parse the 10 million words, or you do simple context extraction, like if you're doing distributional similarity, then the parser comes out in front. But then the raw text guys go, well, I can just do 10 times or 100 times as much data. That's why you want to parse it. You can just throw it the entire web, and then you can say, well, you can't get any more data now. I've got all the data too. Now let's actually look at what those numbers look like.
What do you think it would take to get us past this discussion?
Which bit?
So, well, you know, I wrote a paper a while back called Good Applications for Crummy MT. And the thought was that, look, of course it would be nice if X worked better than it does. But everybody who's working on X wants to work on making X better. But maybe what we need to do to get this question of what is it good for is to get something, it doesn't even have to be state of the art, but something out into the hands of a lot of people in a way that isn't too onerous for them. Now I'm wondering if just putting up on the web the parsed Wikipedia, as it is today, in some form, it just says, and in some format that isn't too onerous to work with. And even parsed trees are kind of work with, right? If there is some way to just put it out there, then maybe people would do something with it as is. If there's some way to give people a tool that they can run almost anywhere with a pretty standard API, it doesn't require more than clicking one button download to sort of get instant gratification. Right? That would be useful. If I need to install a cluster and buy a couple $1 million of equipment and all this just to try it out, probably a very limited audience.
Yeah.
But I'm wondering if the problem is, maybe the problem is this stuff doesn't work, but maybe the problem is something else. Now, on the issue of sort of evaluation, we've had there seems to be this sense that everything's getting better, but I have this stinking suspicion the problems we were worried about decades ago were not actually any better than they ever were.
Yeah.
Say on something like conjunction. And I don't know how to express that. And the numbers go up and up and up, but are we actually doing better?
Well, I mentioned this evaluation that Laura was presenting at MNLP in Singapore. We created this unbounded dependency test suite, and the best score we got was 50%. So we're trying to argue that 92 parse eval scores are just not very good representative of how good parsers are. I mean, of course, that was cheating. It's an objective measure, but it just sort of overstates how good they are. Yeah. And if you're interested in unbounded dependencies, and we argue in the paper that you should be, then parsers are just hopeless at them. And those are the kind of things that people were interested in 30 years ago, and we're not much better now than we were then.
But we're really good at determiner relationships now, right? Something else, some boring bit has got to have been going up for those numbers to go up, and the question is whether those easy bits are in fact useful for any applications, or whether we are just kind of...
Well, is it that the pen tree bank and the current metrics really make you work on something that's not mission critical?
Yeah, well, local dependencies, for example. Absolutely. That's all they measure, the parse eval metric.
Yeah, and the other big case is the domain adaptation problem, right? The fact that we haven't had multiple domains has basically meant that the biggest problem of all, the fact that the performance typically drops off so rapidly when you go anywhere else, even to the New York Times.
Going from Wall Street Journal to the New York Times is a huge drop.
No, exactly, but all of...
lose all those dollar amounts, right?
So, it's...
Suddenly it shows a liberal bias.
They did it too. Damn liberals.
So I think things like that, I actually think domain adaptation is one of the things that if we had more data sets, or if we'd had more data sets for longer, we would have lower scores because we would have remembered that that's a hard problem that we haven't really worked out yet. And bio is the only area that's kind of suddenly made that interesting, I think. And this is one of the reasons why we like having this wiki data, is to try and open that question back up.
What do we take to get the stuff? Is the state of the art good enough for anybody?
Well, QA systems are using it.
So what would it take to make it easier for people to plug in?
Well, I guess past versions of the entire test collection would be the thing that people would need. And
is that hard to come by?
Well, Trek up to now, and I guess now TAC or whatever it's called, hasn't traditionally sent out process stuff. The most they've ever done is send you out a list of the top 1,000 documents that match some set of queries that they generated from the question. So the competitions don't tend to give you much infrastructure to get started with.
Well, is there room for one individual player just to put up a post?
Yeah, I guess. Yeah, a lot of this just comes down to practicalities. I think that the data sets and then doing the processing and so on just hasn't happened. And for us, I've spent a fair bit of time making the parser friendlier, but you still end up getting a huge number of requests from people that want to run it on a VAX or on a Windows machine. And just supporting that and making it easy for everyone to be able to use it is still a bit of a challenge, and it's not the kind of thing that results in publications, so it tends not to happen as much.
Actually, though, distributing a tool that gets widely used will get you more citations.
Yeah, that's true. Yeah.
Let's see if there's a question from someone who hasn't asked anything yet. Okay, you can go ahead.
Kind of a practical issue. The super tagger, I was wondering, is it an increment? Can it be run in an incremental mode, or does it require the entire sentence before it starts giving any results?
Right. So in the version that runs in the parser, it takes the whole sentence because it's doing forward backward over the whole sentence. But there are other modes that are implemented in the parser. For example, a greedy mode that just takes the best possible option for the previous two rather than all possible sequences, and that you could run incrementally. Yeah. In fact, it'd be pretty easy to change the code to do that.
So one last concluding remark and then we close.
Oh, we won't talk about
I would like to ask one more thing.
All right, make it short.
It's short. If you decided to do your statistics by length of sentence, until a certain point, you would have 0 errors. I would hope.
3, yeah.
Well,
in other words, there would be times, there would be lengths for which it would be, let's say, almost completely reliable. Wouldn't that be interesting?
Yeah, it'd be pretty short.
yeah, because incredibly short. Because as soon as you get a coordination in there or a PP attachment, you're in dangerous territory again. So it's got to be short enough that you can't have either of those.
Food and drug administration.
Yeah, exactly.
4 words. What are you going to do?
Well, James had a nice short example too. That his second case wasn't that long, so it fitted on the slide, but the parser still got it wrong because it had a slightly interesting coordination.
A method for food and drug would work. I mean, the engram and that.
Okay, so last comment.
Last comment.
I'd just like to thank everybody for coming along and the interesting questions and comments.
I'm happy with Steve's last comment.